Design considerations, lecture hall. Acoustic design. Recommended reverberation time is 1 second. The North Carolina level should not exceed 25 to 30. The front wall and ceilings can be reflective, enabling sound to reach everyone. Absorptive material on the back and side walls will help reduce the reverberation time and unwanted reflections. Try to avoid parallel surfaces which can cause flutter echoes. Consider splayed side walls. Lecture halls must be fitted with sound-reflecting elements above the speaker. The ceiling can be created as a separate shape that prevents the sound from being reflected back to the speaker. Ceilings should be sloped or stepped and primarily of a hard surface. Acoustical treatment for the ceiling, if required, should be installed around the perimeter of the sides and rear in the form of a U with front and middle sections of hard-surfaced, sound-reflectant materials. Walls should have a STC rating of not less than 50. Walls must extend to floor above or to the roof construction, and not stop at the ceiling. Partial wall surface treatments should be considered as an alternative to ceiling treatment. The back wall may not exceed to be 50 to 100% covered with acoustical absorption materials. Ambient sound levels measured at 4 feet above the floor at all points throughout the room and must have North Carolina rating of more than 35. The mechanical system should generate a background noise of not more than NC 15-20. For lecture halls, noise limits of 35 decibels A, or 30 decibels A, are recommended. Design considerations, classroom. Acoustic consideration. In a classroom, it is important to ensure good speech and listening comfort. The most important aspect in achieving listening comfort is the audibility and clarity of consonants. In addition, interfering noise must be reduced so that it does not drown or mask the relevant sound. Speech comfort is ensured by creating a sense of reverb in order for the rhetoric effects. If too much sound is absorbed, the rhetoric effect of speech will disappear, and if little sound is absorbed, the noise will impede the listening comfort. Acoustic design. Rectangular room, 50 to 70 square meters. Ceiling height -3 meters maximum. Room dimension may not be close to or exceed 1 to 2. Ceiling. Acoustic materials with sound absorbing and diffusing properties as well as a small amount of reflection. These numbers presume the use of noise reduction coefficient, NRC, 0.55 to 0.65. The acoustical tile should be arranged in the form of U around the perimeter walls. Sound absorbing materials with diffusion characteristics. STC not less than 50. Walls must extend to the above floor PR to roof and not stop at ceiling. This will reduce noise transmission. Higher STC ratings and special wall construction details must be included whenever classrooms are located to adjacent or below restrooms, mechanical rooms, elevator shafts, athletic facilities or other sources of high noise transmission. Concrete masonry units may be used but may have to be covered with another finish in order to provide proper acoustical treatment. Folded walls are extremely undesirable and should not be used except under very extraordinary circumstances. Mechanical system. This supports general-purpose classrooms should generate a background noise of not more than NC 35. The air changes and circulation of air as per ASHRAE standards is a critical factor in instructional spaces. This must be achieved with effective control of HVAC system-generated background noise. For large rooms such as school halls, additional factors need to be considered in relation to the direct sound. First, the seating plan should be arranged to fall within an angle of about 140 degrees subtended at the position of the speaker. This is because speech is directional, and the power of the higher frequencies on which intelligibility largely depends falls off fairly rapidly outside this angle. Secondly, sound is weakened as it passes over seated people at grazing incidents. Therefore, if possible, listeners should be seated on a rake where a clearance of around 100 mm is provided between the sightline from one row and the sightline from the next. See figures A and B. It is known that if people cannot see the speaker well, they will not hear well either. It is frequently necessary in schools to have a flat floor in a school hall. In these cases, Speakers should be raised on a platform which is sufficiently high to ensure that minimum clearance is obtained at the rear rows. The direct sound from speaker to listener can be enhanced by strong early reflections that arrive within 50 milliseconds. See Figure D. These early reflections increase the loudness of the direct sound and therefore increase speech intelligibility. They are particularly useful at the furthest seats where the loudness of the direct sound has been reduced by distance. To provide reflections within 50 milliseconds of the direct sound, hard surfaces must be located within a certain distance of the speaker and listener. In most rooms, the center part of the ceiling is the most important reflecting surface and should be of hard, sound-reflecting material. Other useful surfaces providing early reflections are side walls near the speaker, overhead reflecting panels and angled ceiling panels. The additional path traveled by the reflected sound should be no greater than 17 meters more than the direct sound path between speaker and the seating area where the reflection arrives. See Figure. Design considerations. Concert halls. The reverberation time will depend on what type of concert is performed. For classical or orchestral music, a higher reverberation time would be appropriate, approximately 2 seconds. For rock concert, a lower reverberation time would be appropriate, approximately 1 second. This only applies for indoor venues. It is vital to control the reflections from back wall. If not, the sound could reflect off the back wall and slap back to the presenter. This won't impact the audience but could be disastrous and distracting for the people on stage. It is necessary to splay or tilt the rear wall to avoid slap back. A concave wall could compound this problem. If not, it could be treated with absorptive material. Stage area might have higher ceiling than rest of the auditorium, so more absorptive material might be required in this area. Also, the rear wall and some part of side walls could be treated with acoustically absorptive materials. Concert hall acoustics focuses in the design of spaces for live music events. Concert halls are usually used for music performances. Basic shape to design concert hall are shoebox style, fan-shaped, vineyard shape. Shoebox style. It is a simple rectangular room with some balconies. The design is simple, but if not carefully designed it can have problems with flutter echoes. The narrow walls provide spatial and dynamic responsiveness, which naturally leads to highly expressive music with noticeable contrasts. This is optimized when these side walls have a structured or textured finish, promoting reflections to all areas of the room equally. Fan-shaped hall. Fan-shaped rooms can accommodate a large number of attendants while keeping a frontal view of the performers. At the same time, they are not prone to flutter echo because of non-parallel walls. The very wide, non-parallel walls result in sound being reflected towards the back of the hall, rather than at the audience. The central areas of the hall receive very few early sound reflections, which can be perceived as a lack of sound clarity. Vineyard style. Vineyard-style rooms are named so because the seating sections resemble slopes in a vineyard. This type of room has many advantages. It is visually interesting. The irregular pattern helps to avoid issues like fluttering echoes and focusing. The sound experience at the back of a shoebox hall can be enhanced by limiting the dimensions of the auditorium. This can avoid lateral reflections arriving too late, decreasing clarity of sound, or too early, masking the direct sound. Incorporating irregular surfaces on the side walls helps to provide a more diffuse sound environment with more blended, less discrete sound reflections. Whilst shoebox halls are restricted in seat capacity, fan-shaped halls are a good alternative when there is an aspiration to accommodate large audiences. The lack of clarity and envelopment associated with this hall typology can be overcome by optimizing the shape of the side walls to direct reflections towards the audience. Vineyard halls can generally accommodate larger audiences than shoebox halls, typically 3,000 seats. However, the audience size should still be limited to avoid sound from becoming too weak. This can be achieved by restricting the length and width of the hall. Different types of acoustic treatment for music rooms. Design considerations. Cinema hall. Recommended reverberation time is 0.8 to 1.2 seconds. Background noise levels should be kept to minimum. 3 primary potential noise sources are mechanical equipment, HVAC, Noise from adjacent theaters and lobby and outdoor noise. Noise from lobby area can be disruptive. Should properly seal the openings and doorways. Excessive room length should be avoided. A common and often ineffective practice is to use absorptive materials only on the back wall of cinema. This is meant to reduce slap back. But slap back impacts the performers, which in this case are actors on a movie screen. Primary concern should be given to the audience. Although absorption on the rear wall is necessary, the critical areas are the side walls, except possibly those closest to the screen should be absorptive. Design considerations. Auditorium. An auditorium is a large, enclosed room built to enable an audience to attend live lectures, stage performances, concerts, and other gatherings. There are many types and forms of auditoriums that can vary depending upon the type of function, purpose, volume, size, and shape. For example, auditoria spaces suitable for music will be different from spaces for drama, dance, music theatre, opera, or even conference use. The scale of space in terms of seating capacity may further accentuate the form of the auditorium. Auditoriums typically features a stage or platform for speakers and performers, backstage area for performers and their team, seating for the audience, and acoustics designed to enhance the sound quality of the performance or presentation. It is basically a large room or space that is used to accommodate an audience in a building, which can be of any type. All the seats in the auditorium face the stage. Auditorium design consideration/parameter. Site selection and planning. The location of an auditorium is determined by many different factors, some of which may be mutually contradictory, but a compromise must be reached between the various concerns involved. The issue of noise is vital to consider. A noise survey of the site should be made in advance so that noisy locations are avoided where possible. Size and shape. The size should be fixed in relation to the number of people required to be seated. The hall's floor area, including gangways, but excluding the stage, should be computed at 0.6 to 0.9 square meters per person. The hall's height is controlled by several factors such as ventilation, the presence, or lack, of a balcony, and the sort of performance. The average height for small halls ranges from 6 meters to 7.5 meters for large halls. Auditorium standard area per person or seats should be between 1.5 to 2.0 square meters. Visual limitations. For drama, the most important thing is to recognize the facial expression and act of the actors. That's why the most distance ought to be 20,000 millimeters, 70 feet, from the setting line of the proscenium stage or the geometric center of the open stage. For opera and musicals, here the facial expressions and other things are not critical. That's why the distance can be 30,000 millimeters, 100 feet. For dance performances, the facial expressions are less important, but the audience should appreciate the whole body and discern choreographic movement patterns. That's why the distance should not exceed 20,000 millimeters, 70 feet. For conferences, speakers, and lecturers, there are two scales. The first captures the facial expressions that restrict them to 2000 millimeters, 70 feet, and the second is a large scale where facial expressions are not necessary, just the audiovisual projection. Oral limitations. For drama, opera, and classical music, amplification is deprecated, but it is acceptable for variety and pantomime, and essential for rock music. For amplified sound, the auditorium requires a dry or dead acoustic with no reflected sound from the platform or stage and limited or no reverberation. Loudspeakers are positioned to provide full and even coverage of the audience. The volume and quality of the unamplified sound are dependent on the volume, shape, size, and internal finishes of the auditorium and its resultant reverberation time. As an initial guide, a volume in the order of 10 cubic meters per seat should be allowed, but the dimensions and acoustically reflective surfaces of the space for music must also be considered. Recommended reverberation time is 1.0 to 1.5 seconds, might be higher for some auditoriums. Although the seating area will provide absorption, thereby reducing the reverberation time, absorptive materials are to be added to the other surfaces within the space. It is vital to control the reflections from the back wall. If not, The presentation could reflect off the back wall and slap back to the presenter. This won't necessarily impact the audience, but could be disastrous and distracting for the people on stage. Because of this, it's usually necessary to treat the back wall with an absorptive material. A concave back wall could compound this problem. If not, it's imperative that it be treated with absorptive material. Splay or use irregular surfaces on the walls to avoid flutter echoes. Parallel reflective surfaces can allow sound to back and forth between the surfaces. Noise from the lobby area can be disruptive. Be sure openings such as doorways are properly sealed. Consider a vestibule door system. Persons seated deep under a balcony might experience auditory distortion. To avoid this, the balcony should be no deeper than twice its height. Ideally, the balcony should not be any deeper than its height. Even if everything else is controlled perfectly, the space might not be usable if the background noise, for example HVAC system, is too loud. For good design, the North Carolina level should not exceed 20 to 35. When specifying North Carolina, specify an actual rating, such as NC20, rather than a range, such as NC20-30. Although specifying a lower number will ensure minimal background noise, it might be cost prohibitive to achieve. Design of large auditoria for music and speech. 1. To design a concert hall with a large volume, 10 cubic meters per seat, and to reduce the volume of the auditorium when needed for speech. This approach is recommended when the overwhelming requirement is for a good musical acoustic, with a relatively small proportion of theater or other speech use. Unless the volume can be reduced substantially, this approach requires large amounts of absorbent material to be deployed, which in turn can reduce loudness to the extent at which a speech reinforcement system is needed. Nearly all auditoria adopting this approach depend on high-quality speech reinforcement systems, which are difficult to design in a reverberant hall. 2. To design a small volume, not more than 6 cubic meters per seat, with acoustics suitable for a theater, with additional reverberant volumes accessed by openable flaps or movable ceilings. As the volume needs to be increased by up to 80%, with reasonably even distribution of absorption. 3. To design to a compromise volume and RT, often with curtains or other movable acoustic material to provide some variation in RT. The result tends to be an auditorium which is acceptable for a range of uses, but not particularly good for any of them, especially music. Very large areas of curtain are required to have any significant effect in a large hall, and these will have relatively little effect at low frequencies, resulting in a room that is either boomy for speech or dead for music. 4. To design a small volume, 6 cubic meters per seat, with acoustics suitable for a theater, with an electroacoustic enhancement system to introduce more reflected sound. These systems were originally designed to enhance the acoustics of naturally poor auditoria, but their success has recently led to their being built into new auditoria where a wide range of acoustic conditions is required. These systems require loudspeakers in the auditorium's side walls and ceilings. Sound level meter. Sound level meter, SLM, is an instrument, commonly handheld, that is designed to measure sound levels in a standardized way. It responds to sound in approximately the same way as the human ear and gives objective, reproducible measurements of sound pressure levels. A sound level meter comprises a microphone, a preamplifier, signal processing, and a display. The microphone converts the sound signal to an equivalent electrical signal. The most suitable type of microphone for sound level meters is the condenser microphone, which combines precision with stability and reliability. The electrical signal produced by the microphone is at a very low level, so it is made stronger by a preamplifier before it is processed by the main processor. Signal processing includes applying frequency and time weightings to the signal as specified by international standards such as IEC 61672-1, to which sound level meters conform.